Okay, now we are going to do exercise 5 and exercise 6. So let's start at exercise 5. We are going to consider the random variable x taking its values. Okay, consider the random variable x taking its values in the sample space -2, -1, 0, 1, 2 with probability mass function f(x) equal 5 minus 2 absolute value x divided on 13 for x element in -2, -1, 0, 1, 2 and 0 otherwise. Okay. Remember, what we mean with the absolute value. It's actually just absolute value of -2 is 2, and absolute value of 2 is 2. Okay. Verify that f(x) is a probability mass function. In example, that f(x) is bigger or equal 0 for all x, and that the sum of all these f(x's) is equal 1. And we will do that. So let's calculate f of 1. That is 5 minus 2 absolute value 1 divided on 13. This is nothing else but 5 minus 2 times 1 divided on 13, which is 5 minus 2 is 313. And we can do this for all of the possible values in the sample space. So let's say f of 2 is 5 minus 2 times absolute value of 2 divided on 13 is equal 5 minus 4 divided on 13, which is 1 divided on 13. And then we can go take f of 0, which is 5 minus 2 times absolute value 0 divided on 13, which is 2 times 0 is 0, so this is 5 divided on 13. And we can take 5 minus 1 equal 5. F of minus 1 equal 5 minus 2 times absolute value of -1 divided on 13, which is 5 minus 2 times absolute value of -1 is 1 divided on 13, and we get 5 minus 2 divided on 13 is equal 313. And in the end we have, for -2, 5 minus 2 absolute value -2 divided on 13 is equal 5 minus 2 times absolute value of -2 is 2 divided on 13, which is 5 minus 4, which is 1 divided on 13. And this we can collect in a table. So we could have like this, x here and f of x here. And we could have -2, -1, 0, 1, 2. And we see that the probability of minus 2 is 1 divided on 13, of minus 1 is 3 divided on 13, and with 0 is 5 divided on 13, 1 is 3 divided on 13, and 2 is 1 divided on 13. We see that this satisfies we see that this satisfies f of x, the sum f of x, x, sorry, I have to, so we see that this satisfies that that all f of x is bigger or equal 0, and 2, the sum x element in sample space f of x is equal f of minus 2 plus f of minus 1 plus f of 0 plus f of 1 plus f of 2, which is like equal 1 divided on 13 plus 3 divided on 13 plus 5 divided on 13 plus 3 divided on 13 plus 1 divided on 13, which is actually 13 divided on 13 is equal 1, which we were supposed to show. Then we can go to B, and suppose x1 comma x2 comma xn are n equal 130 independent copies of x, sketch the histogram. Sketching the histogram. Of what we expect. Expect it to look like. In a perfect world, we will get minus 2. We should get 113 times 130, like 10 times. Minus 1, we should get what was the probability for minus 1? That was 3 divided on 13. 3 divided on 13 times 130, which is 30. And so on. So then we'll expect 2. We should get 113 times 130 equal 10. So the histogram should be looking something like this. This is a frequency histogram: 10, 20, 30, 40, 50 frequency, and here is x, and the values is minus 2, minus 1, 0, 1, 2, minus 2, 10, minus 1, 30, 0, 50, 1, 30, and 2, 10. So, like this. You could actually also make a density plot here. How would that look like? Still x along this line. So here is density equal false. Here is density equal true. And here is 1, 13, 2, 13, 3, 13, 4, 13, 5, 13. Minus 2, 1, 13, minus 1, 3, 13, 0, 5, 13, and calculating the area under this histogram should give an area of 1. You could try. So that's B. And then C. Compute the expectation x. So the expectation of x is equal the sum x element in the sample space x times the probability of x. Or let's write this way this time. We got the sum I equal 1 to 5 x I times the probability of x equal xi. So this will give, and let x1 then be minus 2, so minus 1 x2, 0 x3, and so on. So then we have, sorry, we don't use p in this exercise, so let's do it with the right notation. So x element in x times fx, that's the expectation, and the sum is then minus 2 times the probability of minus 2 plus minus 1 times f minus 1 plus 0 times f of 0 plus 1 times f of 1 plus 2 times f of 2. And this gives minus 2 times 113 plus minus 1, that's actually minus 1, times 313 plus 0 times 513. You can see the numbers here. Here we got 513 for 0, plus 1 times 313 plus 2 times 113. And then we get minus 2 minus 3 plus 0 plus 3 plus 2 divided on 13, which is equal 0 divided on 13, which is 0. So that's the expectation. And then we get a lot of code in Python. So let's now look at the code for FEM5D. So that's just Python. And we are just going to interpret the code. And you should try out with the different numbers, especially for the end sequence and the subsims, to totally understand what's happening here. But I will guide you through one example. So here we have, first we define this probability mass function. And that is the probability mass function we have been used now in exercise 5. So this is well known. And then here in line 32, that is our sample space in the sense that x is taking values minus 2 or minus 1 or 0 or 1 or 2. N sequence in line 33 is defining how many numbers we are going to draw from the sample space with the defined probability distribution f of x before we take the mean. And it's a sequence because when we are going into this for loop later, n can be first 1, and then it can be 2, and then 3, and then up to 200. So n will be different from every time it goes into the outer for loop. But remember, it's how many numbers we're going to draw from the sample space with the defined probability distribution f of x before we take the mean. That's the point here. Subsims, that's how many times we will draw n numbers and calculating the mean before plotting the histogram. You can think of this as the total frequency of the histogram. Here we just have put up the expectation to the random variable x, and this should be 0 because we have calculated that just in exercise 1c. So if you just run this command and print it, you will see that this is 0. Okay, so now we have defined what we have to define, and then we have to understand this double for loop. So first time we are in the outer for loop, n is equal 1. And where is n in the here you can see where we use n. That's in the second for loop. So first time we are in the outer for loop, n is equal 1. And the histogram will be very spread out. Second time n equal 2, and so on. So it should be clear that when n goes up, every mean we calculate should be closer to the expectation 0. And the histogram will tighten around the expectation 0. Be sure you understand this. You have to try out with changing the end of n sequence, I think. Especially how big n can go. Try with 2, 5, 10, 50 and understand what's happening. I will do it a little video now. So let's make this let's make it to 5 then. And let's run it. So now I got 4 histograms because we have range from 1 to 5. N can be from 1 to 5. That will be 1, 2, 3, and 4. So first we go into this outer follow-up. N is equal 1. Then we draw 500 numbers and calculate. Then we go into the second follow-up and draw 1 number and take the mean of it. And we do this 500 times, so we have 500 means of 1 number. But that's actually 500 numbers, because the means of 1 number is the mean of is the same as the number. So first time we have 500 means, or let's say 500 numbers from our distribution. And we know that these numbers has to be -2, -1, 0, 1, and 2. And since we have 500 of them, it's pretty much, and they will be spread out pretty much as how we expect the histogram to look like. And we have actually just drawn this histogram, and we remember that it looks really much like this. But the second time we go into the outer follow-up, n is equal 2. So then when we then go to the inner follow-up, we draw 2 numbers before we make the mean. And this will do 500 times, and then we have 500 means of 2 numbers. And of course, and the next time we have, when we go to the outer follow-up, n is equal 3, and we take the mean of 3 numbers. Next time we go through the outer follow-up, n is 4, and let's think about n4. Then we go into the inner follow-up, and then we draw 4 numbers and take the mean. And this we do 500 times, such that we have 500 means of 4 numbers. And we can see somehow that something happening here. As n goes up, the histogram tightens around the expectation 0. And this you should understand yourself, think about it. But let's make this more clear by let the n goes up to 20. Okay, then I run the code again. Now we have 19 or 20. So let's see where it starts. Here it starts. So first we know n is equal 1, and we have 500 numbers when n is equal 1, and it should be spread out like this. Next time n is equal 2, we can see it 3, 4, 5, 6, 7, 8, 9. Now n is 10. Here we have the mean of 10 numbers 500 times, and the histogram of these 500 means. And we can see it tightens around 0. And if we now use the code as it was given, with n equal, with the maximum at 201, that's pretty much, and it takes some time. So I don't know if we want to wait for it, but we can try. So I run it now. So now we have to wait for 200 histograms. Every histogram having 500 means represented. But the first histogram just of 1 number, the second of 2 numbers, the third of 3 numbers, and the last one of 200 numbers. And you can stop it here, you see. but I don't stop it. I'm patient, and wait. And when this is working, actually we could start at exercise 6 because that's the last one. So let this work and go to exercise 6. So here is exercise 6. I just take some concrete information we have been given. And we are going to toss coins. Tossing coins. Suppose you have a coin whose probability of showing heads equals theta. Some unknown parameter. Okay? We represent one toss of this coin by the random variable x equal 0 if tails and 1 if heads. Which means that the probability of x equal 1 is equal theta. So this is what we are going to work with now, but let's go back to the Python code and see what's happened here. Now we have, as you know, 200 histograms. I don't know if you can see everybody here. Maybe, maybe not. Yes, we could actually. Here. As usual, the first one is always 500 numbers drawn from the sample space with our probability mass function. And since we just draw one number 500 times, we will get some -2, some -1, some 0, some 1, and some 2's. And if everything is perfect, 113 should be -2, 313 should be -1, 513 should be 0, and so on. But then in the next histogram here, we have, or not the next, let's see, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here we have drawn 10 numbers and found the mean 500 times. So this is actually an histogram over 500 means of 10 numbers drawn from over sample space. And we can see it tightens around 0. And be sure you understand why. And we see how this tightens more and more when n is increasing. And here we see it's very close to 0. Okay. That's enough of that one. So let's now go back to the last exercise of this homework 3, where we are going to toss a coin. That is a well-known thing to do. And we know that the probability of showing head is equal theta. So that's our start here. So the probability of x equal 1, that's the same as showing head, is equal theta. That's what we have in the last line here. So then we can go a little further, because we are not just interested in when it's ahead. We decide to toss this coin until we get a heads up. Then stop. By so deciding, we can define a new random variable. We therefore define a new random variable y equal the numbers of tosses until we get heads up. So example, if we toss first tail, second tail, and third head, y would be equal 3. Because we had to toss 3 times before we got ahead. Okay. A. We are now going to show what's the probability of y equal 3 is. But y equal 3 is actually the same as the probability of x equals 0. That means actually tail. Remember, x0 if tail, and x equal 0 next time, tail, and then x equal 1 head. And this is the same as the probability of x equal 0 times the probability of x equal 0 again times the probability of x equal 1. But what is the probability of x equals 0? That is theta. No, that is 1 minus theta. So, and again 1 minus theta. And what is the probability of x equal 1? Yes, that is theta. We got it here. Probability x equal 1 is theta. Then probability of x equal 0 is equal 1 minus theta, which we have used. So this last one is theta. So this is nothing else but 1 minus theta in the power of 2 times theta, which we was supposed to show. So then we can, what is the probability of y equal 4? Probability of y equal 4, that's of course the probability of x equals 0, and x equals 0 again, and x equals 0 again, and then x equal 1. Which is equal the probability of x equals 0 times the probability of x equals 0 times the probability of x equals 0 times the probability of x equal 1, which of course is 1 minus theta times 1 minus theta times 1 minus theta times theta, which is 1 minus theta in the power of 3 times theta. B. Explain why the natural space in which y takes its values is 1, 2, 3. Y element, it could be 1, it could be 2, it could be 3, it could be more. It could be actually almost infinity. That's because we never know. We never know when we get the heads up. C. Derive an expression for the probability mass function. So we are going to derive an expression for this probability mass function defined by f of y equal the probability of y equal y. This is the probability mass function of a geometric series. I don't think I will talk so much about that. So what must this function be? Okay, let's try to think. We got f of y equal the probability of y equal y is equal, and we know that we will first have tails y minus 1 times, and we stop when we get a head times theta. Let's check it that this is correct. Let's now do f of 3, probability of y equal 3. That's 1 minus theta in 3 minus 1 times theta, which is equal 1 minus theta in the power of 2 times theta, which was what we found just a few seconds ago. And let's also check f of 4, or the probability of y equal 4, which we also checked a few seconds ago. This is 1 minus theta in the power of 4 minus 1 times theta, which is equal 1 minus theta 3 times, tails, and in the end a head. Perfect. So this must be correct. Then we go to D. Okay, I can write here probability mass function. Probability mass function for a geometric series. Geometric distribution. So that's just a name. D. And now we're going to verify that we have an verify that what are you saying here? Okay, but we're going to verify that this f of y is a probability mass function, and it's two demands. One, all the probabilities have to be greater than 0 and or equal to 0, and the sum of all the probabilities has to sum to 1. So let's do that. It's obvious that all the probabilities has to be between be bigger or equal 0, because 1 minus theta is positive, and when you take it in some power, it will still be positive, and theta is positive, so it must be fulfilled. But now let's check the more interesting thing here. That is that the sum I equal 1 to infinity, the probability of y equal yi is equal 1. That is what we have to check. So then we have to write out this sum. We know that the sum I equal 1 to infinity, probability of y equal ye is the same as the sum y equal 1 to infinity, 1 minus theta in the power of y minus 1 times theta. So now I just replaced this probability function with what it is, and I have changed the limits because of the change of notation. So it's not I in the second here, it's a y. And this is the same as the sum y equal 1 to infinity, 1 minus theta in the power of y times 1 minus theta in the power of minus 1 times theta. Remember, two in x plus y is 2 in x times 2 in y. So therefore 1 minus theta in y minus 1 has to be 1 minus theta in y times 1 minus theta in minus 1. And then we can write this as the sum y equal 1 to infinity, 1 minus theta in the power of y times, and this second term here, or factor, can be set as this. Remember, x in minus 1 is the same as 1 divided on x times theta, And these two last factors is just constant, so I put them outside the summation sign. So I get theta over 1 minus theta, sum 1 minus theta in the power of y. And now just we have a hint in this exercise. So using the hint, and the hint is like this: sum k equal 0 to infinity is equal x in the power of k is equal 1 divided on 1 minus x. But now I regret myself for doing something here. Because but we learn more then, so let's just continue. Then we have 1 minus theta here, and y equal 1 to infinity. But we shouldn't have 1. We should have from 0. So I changing the limit here. Why do I need 0? That's because of the hint, which uses 0 here. But when I put the limit down 1, I have to start 1 lower, 1 higher here. So this will get like this. And then I have to do the same once more. Y equal 0 to infinity. 1 minus theta in y times 1 minus theta. But then I see that I can just take this against this, and I got theta sum y equals 0 to infinity, 1 minus theta in y. And now I can use the hint. That this sum is actually nothing else but 1 divided on 1 minus x, but x is 1 minus theta. So then we get 1 minus theta here. And we get theta times 1 divided on 1 minus 1 plus theta, which is equal theta divided on theta, which is equal 1, which was what we had to show. Okay, let me take you through this once more. It's obvious that the sum of all the probabilities has to sum to 1. So that is what I'm going to show here, that this sum is 1. So the first I do is replacing the probability function with its really function. So this line is perfect. But then I don't like this minus 1. And so I just write it like this. So this is the same as these two. That should be understandable. And then I just put this under in the denominator, and that makes the exponent positive. So we get this line. That should also be okay. And then I put all these constants outside. That should be okay. And then I do then I change the limit here from starting at 1 to starting at 0. And why do I do it? Because the hint is telling me that I start at 0. But when I start at 0, because here the first element of the sum is 1 minus theta in the power of 1. So that has to be the same now. And therefore y has to be 0, because then it will be 1 minus theta in 0 plus 1. That is 1 minus theta in 1. So it's still the same. And because it goes to the infinity, it's not a problem here. No problems here. So, and then I do exactly the same as I did a little above here, with this, when it's the minus 1 here, now it's standing plus 1. So that's the same as 1 minus theta in y times 1 minus theta in plus 1. But this one and this one is equal, and I can cancel them out, and we stand with this. But now this is just as the hint, where x is 1 minus theta, and we get that this sum is 1 divided on 1 minus x, but x is 1 minus theta. And we see that this is 1 minus 1 plus theta, and we get theta over theta, which is equal 1. What we were supposed to show. So then it's just E, and then I will just be happy to say, look at the answer in the exercise. Look at the answer in the exercise. Or let it be. Okay, that was it. Next time it's homework 4.